Hypersonic jets represent a revolutionary leap in aviation, designed to achieve speeds exceeding Mach 5, or over 3,800 miles per hour. This incredible velocity promises to drastically reduce intercontinental travel times, shrinking journeys from hours to mere minutes. However, transforming this ambitious vision into a practical reality involves navigating a complex array of technical, financial, and regulatory obstacles. Significant progress has already been made through a series of uncrewed experimental flights, validating key technologies essential for hypersonic flight. The NASA X-43A, for instance, achieved an astonishing Mach 10 in 2004. This groundbreaking test demonstrated the viability of scramjet propulsion, which efficiently scoops atmospheric oxygen for combustion, eliminating the need to carry heavy onboard oxidizers. Building on this success, the Boeing X-51 Waverider flew at Mach 5.1 for over 3 minutes in 2013. This flight further proved the effectiveness of supersonic combustion ramjets, or scramjets, where incoming air is compressed by the vehicle's own speed before fuel ignition. These experimental achievements confirm the fundamental physics of air-breathing hypersonic propulsion. Nevertheless, these successes are foundational steps, still a considerable distance from commercial passenger service. The core of hypersonic flight lies in advanced propulsion systems. At speeds above Mach 5, air-breathing scramjets become highly efficient. Incoming air is compressed and ignited in a supersonic flow, eliminating the need for heavy rotating compressors or turbines found in conventional jet engines. This scramjet cycle significantly reduces aircraft weight and enhances fuel efficiency at high altitudes. Many proposed designs incorporate combined cycle propulsion systems. These aircraft would utilize conventional turbo ramjets for takeoff and initial acceleration, then seamlessly transition to scramjets or even rocket boosters once they reach the necessary hypersonic speeds and thinner atmospheric conditions. This hybrid approach optimizes performance across different flight regimes. Advanced engine concepts are also under development. Rotating detonation engines, exemplified by Venus Aerospace's Stargazer M4, sustain continuous combustion at supersonic speeds. This innovative technology could potentially deliver Mach 9 performance with a remarkable 20% less fuel than traditional engines. Beyond propulsion, material science is critical. The aircraft's skin and engine components must endure extreme frictional heating, reaching temperatures up to 1,000 degrees Celsius. This necessitates the use of specialized materials such as carbon composites, ultra-high temperature ceramics, or advanced metal alloys. These materials often incorporate active cooling channels to prevent structural failure under intense thermal loads. The path to commercial hypersonic travel is fraught with significant challenges. Thermal management is paramount, as sustained hypersonic flight generates immense heat. Materials and sophisticated cooling systems must prevent structural integrity loss at temperatures exceeding 1,000 degrees Celsius. Fuel and infrastructure present another hurdle. Traditional jet fuels struggle to perform optimally at hypersonic regimes. Alternatives like liquid hydrogen offer superior performance, but demand entirely new storage and fueling infrastructure at airports. The financial investment required is staggering. Development and testing alone are projected to cost billions of dollars. Consequently, early ticket prices would likely be prohibitive, initially restricting service to government, military, or ultra-wealthy travelers. Regulatory issues, particularly concerning sonic booms, are also a major concern. Overland hypersonic flight is currently banned in many countries due to the disruptive noise generated. This limitation restricts viable routes primarily to ocean corridors, unless new sonic boom mitigation methods are developed and approved. Finally, safety and certification pose a formidable barrier. Aviation authorities and insurers require decades of proven reliability data before any commercial rollout. Establishing this extensive track record for a completely new class of aircraft will be a lengthy and rigorous process. Several prototypes and concepts illustrate the diverse approaches to hypersonic flight. The NASA X-43A, an uncrewed test vehicle from 2004, achieved Mach 10 using a scramjet. Similarly, the Boeing X-51 Waverider, tested in 2013, reached Mach 5.1 with a scramjet ramjet. Looking to the future, the A-HIM Hypersonic Airmaster is a concept for a hydrogen-powered scramjet aiming for Mach 7.3. Venus Aerospace's Stargazer M4, currently in development, utilizes a rotating detonation engine with a target speed of Mach 9. Hermeus is developing the quarter-horse and Halcyon aircraft, which employ a combined cycle engine to achieve Mach 5, with both military and commercial applications in mind. The initial operators of hypersonic jets are likely to be specialized entities with unique requirements. Military and defense organizations are prime candidates, seeking rapid global strike capabilities and strategic reconnaissance using hypersonic cruise and glide vehicles. Government and VIPs, including heads of state, diplomats, and emergency response teams, would benefit immensely from ultra-fast point-to-point transit. Ultra-high net worth individuals, such as CEOs and celebrities, could also be early adopters, funding initial routes where time is considered the ultimate luxury. Furthermore, space tourism firms like Venus Aerospace and Sierra Space may offer suborbital edge-of-space flights that could double as hypersonic transcontinental services, blurring the lines between aerospace and commercial aviation. Hypersonic jets represent a complex convergence of cutting-edge propulsion, advanced materials science, and sophisticated digital design. While uncrewed tests have successfully proven the core principles, scaling this technology to safe, reliable passenger service will demand decades of sustained innovation, comprehensive regulatory frameworks, and massive financial investment.